Welcome to my channel Phi Concepts CHM. We are going to see about the symmetry elements. Crystal symmetry. Crystals have inherent symmetry. The definite ordered arrangement of the faces and edges of a crystal is known as crystal symmetry. It is a powerful tool for the study of the internal structure of crystals. Crystals possess different symmetries or symmetry elements. Symmetry. Crystals have an ordered internal arrangement of atoms. This ordered arrangement shows symmetry. That is, the atoms are arranged in a symmetrical fashion on a three-dimensional network referred to as a lattice. Crystal faces reflect the ordered internal arrangement of atoms and hence reflect the symmetry of the crystal lattice. Let's first imagine a small two-dimensional crystal, this diagram, composed of atoms in an ordered internal arrangement. All of the atoms in this lattice are the same. For our understanding, this corner atom is being shown as red color so that we can see how the crystal is rotated. If we rotate the simple crystals by 90 degrees, notice that the lattice and the crystal look exactly the same as what we started with. Rotate it another 90 degrees this way and again it's the same. Another 90-degree rotation again results in an identical crystal this way. And another 90-degree rotation returns the crystal to its original orientation, that is this way. Hence, in one 360-degree rotation, the crystal has repeated itself or looks identical 4 times. Hence, we say that this object has four-fold rotational symmetry. Symmetry operations and elements. A symmetry operation is one that leaves the crystal and its environment invariant. It is an operation performed on an object or pattern which brings it to a position which is absolutely indistinguishable from the old position. A symmetry operation is an operation that can be performed either physically or imaginatively, that results in no change in the appearance of an object. There are three types of symmetry operations: rotation, reflection, and inversion. Rotational symmetry. If an object can be rotated about an axis and repeats itself every 90 degrees of rotation, then it is said to have an axis of four-fold rotational symmetry. The axis along which the rotation is performed is an element of symmetry referred to as a rotation axis. The following types of rotational symmetry axes are possible in crystals. One-fold rotation axis, an object that requires rotation of a full 360 degrees in order to restore it to its original appearance, has no rotational symmetry. Example is this diagram. Since it repeats itself one time every 360 degrees, it is said to have a one-fold axis of rotational symmetry. Two-fold rotation axis. If an object appears identical after a rotation of 180 degrees, that is twice in a 360 degree rotation, then it is said to have a two-fold rotation axis. That is 360 degrees divided by 180 degree is equal to 2. Note that in these examples, the axes we are referring to are imaginary lines that extend towards you perpendicular to the page or the blackboard. Four-fold rotation axis. If an object repeats itself after 90 degrees of rotation, it will repeat 4 times in a 360 degree rotation. That is this diagram. Axis of symmetry. This is an axis passing through the crystal such that if the crystal is rotated around it through some angle, the crystal remains invariant. The axis is called n-fold axis if the angle of rotation is 360 divided by n. If equivalent configuration occurs after rotation of 180 degrees, 120 degrees and 90 degrees, the axes of rotation are known as two-fold, three-fold and four-fold axes of symmetry respectively. Reason for absence of five-fold symmetry. Crystalline solids show only 1, 2, 3, 4 and 6-fold axis of symmetry and not 5-fold axis of symmetry or symmetry axis higher than 6. The reason is that a crystal is one in which the atoms or molecules are internally arranged in a very regular and periodic fashion in a three-dimensional pattern, and identical repetition of an unit cell can take place only when we consider 1, 2, 3, 4 and 6-fold axis. Mirror symmetry. A mirror symmetry operation is an imaginary operation that can be performed to reproduce an object. The operation is done by imagining that you cut the object in half, then place a mirror next to one of the halves of the object along the cut. If the reflection in the mirror reproduces the other half of the object, then the object is said to have mirror symmetry. The plane of the mirror is an element of symmetry referred to as a mirror plane. As an example, the human body is an object that approximates mirror symmetry, with the mirror plane cutting through the center of the head the center of the nose and down to the groin. This diagram shown has two planes of mirror symmetry. The rectangle on the left has a mirror plane that runs vertically on the page and is perpendicular to the page. That is this one. The rectangle on the right has a mirror plane that runs horizontally and is perpendicular to the page. That is this one. The dashed parts of the rectangles below, that is this part, show the part of the rectangles that would be seen as a reflection in the mirror. Center of symmetry. It is a point such that any line drawn through it will meet the surface of the crystal at equal distances on either side. This point is the center of symmetry. Since center lies at equal distances from various symmetrical positions, it is also known as center of inversion. It is equivalent to reflection through a point. A crystal may possess a number of planes or axes of symmetry, but it can have only one center of symmetry. For a unit cell of cubic lattice, the point at the body center represents the center of symmetry, as shown in the figure. Combination of symmetry elements. Apart from the different symmetry elements, different combinations of the basic symmetry elements are also possible. They give rise to different symmetry points in the crystal. The combination of symmetry elements at a point is called a point group. The symmetry of the basis, called point group symmetry, refers to all possible rotations, including inversion and reflection, which leave the basis or the crystal invariant. In crystals, 32 point groups are possible. The combination of 32 point groups with 14 Bravais lattices lead to 230 unique arrangements of points in space. They are called as space groups. Thank you for watching my video.